Okay, so how do you actually go from a cool idea to a physical chip? It's a journey, and it really breaks down into 4 key stages. First, we're going to design and simulate our idea. Then, we synthesize it into a digital blueprint. After that, we actually craft the physical layout. And finally, we'll see how to put the whole thing on autopilot.
So, let's kick things off with part 1, from idea to logic. It's pretty straightforward. Before you can build anything, you have to describe what you want it to do, right? This part is all about capturing your design in code and then running it through a virtual gauntlet of tests to make sure it actually works. Your first stop on this journey is probably going to be Icarus Verilog. The best way to think of it is as a friendly flight simulator for your chip design. It lets you write your ideas in the Verilog language and then run them in a totally virtual environment to see if they, fly. It's simple, it's reliable, and it's absolutely perfect for getting your feet wet. But what happens when your design gets bigger, like a lot bigger, when it goes from a simple circuit to a whole complex processor? That's where Verilator just shines. It takes your design and does something kind of brilliant. It compiles it directly into super optimized C++ code. This makes your simulations insanely fast. We're talking orders of magnitude faster, which is absolutely critical when you're testing huge, complex chips.
So really, the choice is pretty simple. If you're learning or you're working on smaller projects, Icarus Verilog is your best friend. It's easy to use, does the job. But when you need to verify a massive design and every second counts, Verilator is the undisputed champ. No contest.
Okay, so a simulation spits out a mountain of raw data. How in the world are you supposed to find a tiny bug in all that noise? Well, you use GTK-Wave. Think of it like an EKG for your circuit. It takes all that data and visualizes it as waveforms, letting you literally see the electrical heartbeat of your design, tick by tick. It makes spotting problems so much more intuitive.
So we've got a design, and it works perfectly in our virtual world. Awesome. Now it's time for part 2, from logic to blueprint. This is where we take that abstract code and turn it into a concrete plan for a physical circuit. This little bit of magic is called synthesis.
And the star of this stage is a tool called 𝐕𝐝. It's like the master architect that translates your high-level Verilog code into what's called a gate-level netlist. Just think of that netlist as a super detailed schematic. It's a list of every single logic gate, all your ands, ors, and nots, and the exact wiring diagram that connects them all together.
Now, before you commit to the very expensive process of actually manufacturing a chip, you might want to test it on some real hardware first. That's where FPGAs come in. These are chips you can reconfigure, and SymbiFlow is the complete open-source toolchain that lets you take your design and run it on real FPGAs, giving you a physical prototype without having to go to a factory.
All right, we have our blueprints of logic gates. Now for part 3, from blueprint to silicon. This is where we take that logical description and start the incredibly detailed, meticulous process of laying out the actual transistors and wires that will be etched onto a real piece of silicon.
If there's one single thing that really lit the fuse on this whole revolution, it's this, the SKY130 PDK. A PDK is basically the secret recipe book from a silicon factory. It has all the rules, all the ingredients you need to design a chip that can actually be made there. These things used to be top-secret, multi-million-dollar assets. And then, Google and 𝐕𝐿SI did something unthinkable. They gave one away to the world, for free.
The impact of this is, well, it's profound. This isn't just a simulation anymore. It's not a textbook exercise. The SKY130 PDK means that students, researchers, hobbyists, pretty much anyone, can design real physical chips that are ready for manufacturing. It is a complete democratization of silicon design. So to create the physical layout, you've got a few key specialists on your team. There's Magic VLSI, which is like drawing with a digital microscope. It's fantastic for learning by placing transistors by hand. Then you've got KLayout, which is your final inspection tool, a high-powered viewer for checking every last detail. And then there's the heavy hitter, OpenRoad. This is the automated factory foreman that handles the really tough stuff, figuring out the floor plan, placing millions of components, and routing all the wires.
Okay, so we've seen all these specialized tools, but what if you could manage the entire project from a single command center? Well, in our final section, part 4, we're going to look at the tool that does exactly that, automating the entire flow from code all the way to a factory-ready design.
Meet OpenLane. The best way to think about this is as the general contractor for your entire chip project. It's basically an automated script that manages the whole process. You feed it your Verilog code, it runs through dozens of complex steps, and then it spits out a single GDSII file. And that one file is the master blueprint you send directly to the foundry to get your chip made.
So you see, OpenLane is really the conductor of the orchestra. It doesn't play the instruments itself. It directs the experts. It calls on 𝐕𝐞𝐳 to handle the synthesis. It commands OpenRoad to manage all the physical design. It uses tools like 𝐘𝐳 for final checks. It just ties everything together into one seamless, automated performance.
So here's the bottom line. Thanks to this amazing suite of open source tools, the entire journey of designing a chip, from writing that first line of code to getting a file ready for the factory, has been completely democratized. That massive financial barrier, it's gone.
So the billion-dollar barrier has been smashed. The secret knowledge is out in the open. The tools are completely free, and they're just waiting there on your computer. The only thing missing now is your idea. So the question is no longer if you can design a chip. The only question is, what will you design first?